All right, in this explainer, we're diving deep into a mystery that's at the very heart of, well, everything: the atom. We're going to trace the story of how we figured out the fundamental architecture of matter, from the very first wild guesses all the way to the strange quantum rules that govern our entire universe. So, let me ask you a question. Imagine you're handed a sealed box. You absolutely cannot open it, you can't see inside, but your job is to figure out exactly what it contains and how it all works. You can, shake it, you can weigh it, maybe shine some lights through it, but you can never, ever look inside. How would you even start? Well, for the greatest minds in science, for literally centuries, that locked box was the atom. It was way too small to see, too fundamental to just crack open. They had to figure it out from the outside in, piecing together these tiny little clues to build a picture of what was going on at a scale that's almost impossible to imagine. So, how did they start? Well, like any good detective story, it all kicked off with a series of first drafts. Theories that got some things right, but really missed the bigger picture. It all started way back in 1808 with John Dalton. He basically pictured atoms as these tiny, solid, indestructible marbles. Super simple, right? But it couldn't explain things like electricity. Fast forward to 1897 and J.J. Thomson discovers the electron. His idea, the plum pudding model, this ball of positive pudding with negative electrons scattered inside. It was a step up, for sure, but it didn't hold up to experiments. And then came the big one: Ernest Rutherford's gold foil experiment in 1911. It showed the atom was mostly empty space with this tiny, dense, positive center, giving us the solar system model. This was a huge leap, but it had one giant fatal flaw. And to really get why that model was so flawed, we first have to properly meet the cast of characters inside the atom. This was the nuclear revolution, where he finally put names to the true components of matter. Okay, so you've got the electron, this tiny, negatively charged particle that's buzzing around, responsible for pretty much all of electricity. Then, right in the center, in the nucleus, you've got the heavyweights, the positive proton and the neutral neutron, which, as its name suggests, adds mass and kind of keeps the whole nucleus from flying apart. These three particles, they make up every single atom in the universe. And this brings us right back to that huge problem I mentioned. If the atom really was like a tiny solar system with electrons orbiting the nucleus like planets, well, the laws of physics, as they were known at the time, made a very, very grim prediction. So here's the crisis. The problem was that any charged particle moving in a circle, like an electron orbiting a nucleus, should constantly be giving off energy. It should lose speed and spiral into the nucleus in like a fraction of a second. Every atom in the universe should instantly collapse. But they don't. The solution, which came from Niels Bohr, was just radical. Maybe the rules inside an atom are just different. He proposed that electrons could only exist in very specific, fixed energy levels, or orbits, and while they're in one, they don't lose any energy at all. And this is the core of Bohr's incredible idea. The best way to think about it is like a ladder. An electron can be on one step, or it can be on another step, but it can never, ever be floating in between the steps. To jump up a step, it has to absorb a very specific amount of energy, and when it falls back down, it spits that energy back out as a specific color of light. This is exactly why different elements glow with their own unique colors. It's like their atomic fingerprint. But the detective story wasn't over, not by a long shot. Bohr's model was an absolute breakthrough, but it was still incomplete. I mean, it worked perfectly for hydrogen, which only has one electron. But as soon as you tried it on more complex atoms, the whole thing just fell apart. And maybe most importantly, it was just a rule. It couldn't explain why. Why were these orbits fixed in the first place? And the next clue, oh man, it changed everything. Scientists finally realized they were trying to apply the rules of big things, like planets and baseballs, to a world that plays by a completely different rulebook. The shocking, mind-bending truth was this: electrons aren't just little particles whizzing around. They also behave like waves of probability. This bizarre discovery led us to the modern quantum model of the atom. And honestly, it's less of a physical picture and more of a rulebook, a set of laws that perfectly describes an electron's energy and where you're most likely to find it. The best analogy? It's like finding an electron's precise address inside the atom. So this address has four parts, what we call quantum numbers. First, you have the principal number, n. That's the main energy level. Think of it as which floor of the building you're on. Then there's the azimuthal number, L, which describes the shape of the orbital. Is it a sphere, a dumbbell? That's kind of like the type of room on that floor. Third is the magnetic number m, which is just its orientation in space. Which way is that room facing? And finally, you have spin, s, which is just a property of the electron itself. So how do electrons actually find their addresses? Well, they follow three surprisingly simple rules. The first one is the off-bow principle. Honestly, it's just common sense. Electrons are lazy. They're always going to fill the lowest energy spots available first. They start on the ground floor of that atomic building before they even think about moving up to higher levels. Rule number 2 is the Pauli exclusion principle, and this is a deep fundamental rule of nature. It says that no two electrons in an atom can have the exact same 4 quantum numbers. It's like saying no two people can have the exact same full address, right down to their name. An orbital can hold 2 electrons max, but only if they have opposite spins. Every single electron gets its own unique identity. And the third and final rule is Hund's rule. This one's easy. If you have a bunch of orbitals with the same energy, think of it like empty seats on a bus bench. Electrons will each take an empty seat before they start pairing up. It's just a more stable arrangement that way. They like their personal space. So we have the particles, we have the energy levels, and now we have the rulebook for how electrons fill them. But why? Why does any of this matter? Because what we've been talking about isn't just some abstract physics puzzle. This is the blueprint for all of chemistry. That quantum rulebook we just walked through literally determines everything about an element. How it's going to react, what kind of bonds it will form, whether it's a solid, a liquid, a gas. Its entire chemical personality is written right there in the arrangement of its electrons. Let's just take sodium as a perfect example. It has 11 electrons. So, following those rules we just learned, its electrons start filling up the lowest energy levels, the first floor, the second floor, and they fill them up completely. But what's left? One single electron, all by itself on the outermost level. And that lone exposed electron is just desperate to react with something, which is precisely what makes sodium so explosive when it touches water. So if you take one thing away from this whole story, it's this. The long journey to solve the atom was really the journey to discover the rules of electronic configuration. Because once you understand those rules, you hold the key. You understand why elements behave the way they do. Electronic configuration is chemistry. It's the whole game. Think about it. We went from seeing the atom as a complete mystery, a locked box, to understanding its weird and wonderful quantum rulebook. We've basically solved the fundamental architecture of matter itself. And that leaves us with a really exciting final thought. Now that we know the rules, what can we build next? What new materials, new medicines, and new technologies are waiting for us to design?